Okay, so again, last time, what we did was we took the Bohr model, right, used it as our starting point, calculated the Rydberg equation. 1 over wavelength is equal to some constant times 1 over n1 squared minus 1 over n2 squared, right, that quantity. And we saw that, as we pull out assumptions, we get closer and closer to reality, but the math gets more and more complicated, right? That was the key part, or the key concept I wanted you to get from that is, Bohr's model reproduces the experimental value, so Rydberg, that constant was experimentally derived, but there was no explanation for it, right? It's just it fits this math. Bohr's model of quantized energy states works out and reproduces from a completely different spot the Rydberg equation. And then if you add the complication of the nucleus, and it's particularly important for the hydrogen atom because the nucleus of the hydrogen atom is a lot less than an electron, right? So this would be your heavier mass, your lighter mass would be sort of moving around it, and you can think of it as like imagining like a binary star where one of them's heavier than the other. They're rotating around each other, and we saw when we added that complication of the nucleus actually moving, right, getting rid of that assumption, that our reproduction of the Rydberg constant became much more close to what we see experimentally. So just a reminder, the Bohr model is essentially like a planetary motion type thing where you have the electron in a defined location moving around in a set orbit, and then depending on the distance, at least according to Bohr, that's what gave the different energy levels. So you would have your nucleus here, n equals 1, n equals 2, and then you got your 2 electrons, and then over here you can have 2, 3, 4, 5, 6, 7, 8, which is sort of explaining your why the periodic table looks the way that it does is from all this stuff, right? The problem with the Bohr model, well, there's a couple problems, right? One is that it only reproduces the values for hydrogen, right? So the Rydberg type equation where we can predict the different bands where they're at, it only works for hydrogen atoms, right? And part of the reason it only works for hydrogen atoms is the complication of all the other electrons, right? For the hydrogen atom, it also works for, I think, a helium plus, where you pulled out both electrons. So it works reasonably well if you don't have electrons interacting with other electrons. But in anything other than hydrogen, you have more than one electron, and so it doesn't work. But it works really well for hydrogen, which sort of gives us credence to using it. You still have the revolving electric charge, right, which causes the problem of there should be energy coming off of it, and so you have a perpetual energy. Violates the first law of thermodynamics. You have an infinite energy source. The electron has a set location and a set direction, and so that would violate Heisenberg uncertainty principle of you not being able to determine the position and the momentum at the exact same time, right? And so this particular model of planetary motion violates the Heisenberg uncertainty principle. De Broglie, so if you remember de Broglie wavelength, came up with a sort of a workaround for this and said instead of it being going around in planetary motions, it's actually a standing wave function. So the electron, instead of being a set location, actually occupies a wave-like behavior in that circular path. So instead of being in one spot, it behaves as though it's a wave going around the nucleus. And so you no longer have a defined position, and that gets around violating the Heisenberg uncertainty principle. It's sort of a way of visualizing the particle wave duality of an electron. It turns out that it's not right, but that was one of the workarounds that they tried, right? So we're going to get into, we're actually, when we hit, I think it's chapter 8 or 9, coming up, we're going to actually graph the orbitals. So, you know, the px, py, pz orbitals, the s orbital, the d x squared minus y squared, we're going to graph those and you're going to see where they actually come from. You know, so the magic behind why does it look the way it does, why has it got a dumbbell, what's the difference between a 1s and a 2s orbital. There's actually a huge difference between them, but they look the same if you look at the books. Right? So we're going to get into all that. But the Bohr model had some issues. So this is where we get into all the different terms and complications. So wave functions, Schrodinger and Heisenberg both came up about the same time with this idea of general quantum mechanics. Right? So those 6 postulates of quantum mechanics, they both somewhat independently came up with the ideas. And the way that they treated the math is different. So Schrodinger used partial differential equations, and Heisenberg used matrices or linear algebra, right? And so different places that you look on the web, some of them are going to treat it with differential equations, some of them are going to do linear algebra. At the time, most physicists used differential equations, right? Diff-EQ gets used a lot. And so the one that primarily gets adopted is Schrodinger's method using differential equations. That's the one we're going to do. And the reason we're doing it is linear algebra is a whole nother beast. Diff-EQ, because you can do derivatives and integrals right from your calc class, we can cobble together enough that you can do Diff-EQ. Right? You have the foundations to understand it, whereas linear algebra, it would take more time. Okay, but if you've had any matrix multiplication in any linear algebra, you could look up sources or swing past my office and we can look together, find some sources that treat it that way as opposed to differential equations. They all end up giving you the same thing, right? They all explain it and you end up with the same answer. It's just 2 different ways of doing the math, okay? Yeah, that covers it. Okay, so Schrodinger's method gets used a lot more, and so that's what we're going to use. Okay. Now, the notes that you might have printed out, they're going to be slightly different from what I have because I decided, went through it again, practiced it, and decided to tweak it a little bit. I've uploaded a altered or an updated version, right? Essentially, there's not a terrible lot different, but there is some differences. But this version is uploaded on your the Blackboard site. So, because matter is behaving as a wave, we need to have some sort of an equation. The Schrodinger equation looks like this, and we will be explaining what all these various terms mean in the coming slides. Right? So H is called the Hamiltonian. There's actually, in classical physics, there's a way to calculate energy using this. So this Hamiltonian itself is not necessarily set in quantum mechanics. It's a different classical way of treating energy. This psi here is the Schrodinger wave equation. E is the energy level of the system. And when we get into the next set of lecture slides, that's when we're going to actually derive this guy and show wave equations and all that sort of fun stuff. Okay? You guys got all that? Yeah? Okay. Now, in terms of interpretation of what a wave function actually is, so the wave function itself should have some sort of a real meaning to it. Why are we using the waves? Well, Born came up with an idea for what the wave function meant. And his idea, it's a central principle of quantum mechanics now, it's that the wave equation so it contains all the information about the system it describes. And that if we square the wave function, or take the square of the absolute value, because in some wave function there are imaginary components. We'll get into a quick review of complex equations where you have a real component and an imaginary component in a little bit. But taking the absolute value of the square gives you the probability distribution function, and the next bunch of slides are talking about what a probability distribution function is. Essentially, it's a statistics thing that tells you the probability of finding the particle at a particular location, in this case. So the wave function itself, non-squared, is called the probability amplitude. So the higher the wave peak is, the more probable, once you square that value, the more probable it is to find the particle there. And similarly, if you have the negative amplitude, because you're taking the square of it, that reflects it up top, right? And so the wave function would have this sort of a wave, a peak and a trough. When you square it, the trough also becomes a peak. Okay? Now the term that we use, because we have complex numbers, is instead of just the square of the wave function, it's the square modulus of the wave function. It's one of the ways that you handle squaring things when you're dealing with complex numbers. We will get into that in just a second. Okay, the key part that I want you to get from here is Born's interpretation of the wave function is if you square it, that tells you where stuff is, right? It gives you a probability distribution function of how probable it is to find the electron or the molecule or the atom at a particular point in space.
So when you're squaring the wave function, you're solving for psi first of the Schrödinger equation, and then squaring it. So we have like h naught or h hat psi equals e psi. So you're first solving for psi and squaring that to get the probability.
It's the psi that fits within that function. So that's psi is an eigenfunction. We're going to get into that. Unfortunately, all these terms are interwoven, and so there's no real good starting point. Okay, the key part, you have a function that describes a wave. Square it, that tells you where stuff is. Okay, so probability distribution function, what the heck it is. Imagine you're running, right? So in 2015, about 7 million people did a 5K race. The average time for the winners is somewhere in the 13 to 15 minute range, which is a 4-minute mile, which is a little bit above a 4-minute mile, but that's pretty impressive. The average pace is more mine, which is a 10-minute mile. So I think that's fast, but that one's insane. Okay, so what we could do is look at the probability of a particular runner. If we just grab someone at random, what's the probability they're going to run at this pace versus that pace, right? And most things in nature actually follow a Gaussian-esque distribution. So you have some people that are crazy fast, some people that are not fast, and then a distribution. Somewhere in the middle, you have the majority of the population. There's a bunch of different ways that we could look at this. So one of the ways you could do it is break it down into 1-minute increments, right? So all the people that fall between the 7-minute pace and the 8-minute per mile pace, right? So the way that you would do that is you take the number of runners times the time of the runner in a particular block divided by the total number of runners to give you the percent that fall within that range, right? So if you have 15 runners that ran in that time space, you take 15 times 7 minutes, add all those together, and then divide the total sum by the total number of runners, and you get the average pace of the runner. Right? So or you could do it in terms of groups. So one, you could do sum up all the runners, one at a time, take each runner times their time, divide by the total number of runners. That makes sense if you have only a couple, right? If you have like 20 people, you can easily do this. But if you talk like Boston Marathon type numbers, then it makes sense to group them into time categories. And then you take the time for that group times the number of runners that fall in that group, divide by the total number of runners, add all those together, and you get the average. It's whether or not you say, you know, this runner did 8 minute plus this runner did 7 plus 8 plus 6 plus 8. You know, add those all together, divide by the total number of runners, or you say, in the group of people that ran it at 8, there were 20 of them, so 8 times 20 divided by 1,000 runners, right? The first method where you're adding each one individually is this top one. The second one where you're saying this is the time block, this is how many people fall in the time block, divide by the total, that's the second method, right? And you can see, you know, if you have 8 runners, typing this into the calculator would be fairly easy. If you break it into 2-minute intervals, you know, this is sort of the distribution you get. You can sort of see that there's a larger peak here, smaller peak here. In the shorter intervals, it's less easy to tell with this small number that there's necessarily a big distribution. If you break it into 100 runners under the same time frame, this one you can easily see that there's some sort of a distribution. Here in the larger categories, it again becomes a little bit difficult to, you know, see what's going on. So working out what blocks you want to do becomes important. And you can see going from the larger blocks to the smaller blocks of time when you have a large data set becomes important. So this is sort of the idea where you could have summations versus integrals, right? This here is more approaching an integral. So what do you actually observe? So this is 10,000 runners in 10-second intervals. You can see you get a distribution with very few people down here, the crazy crazies, and then the people that probably need to practice a bit more over here. So that distribution is called a probability distribution function. So if we take this and try to fit a function through that, so look, you know, curve up and then down, getting a graph that looks something like this, it's called a probability distribution function, right? Most people or most populations, if you're doing any type of a measurement, have some sort of a distribution. So you can have a height distribution, weight distribution, speed of running distribution, right? Almost all distributions are going to have some sort of a Gaussian-esque or bell-shaped curve to them. Now, the thing about a probability distribution function is it's in terms of percent. What percent fall within this category? And so if you take the integral of that probability distribution function from the lowest possible value to the highest possible value, you're capturing 100% of your population. Right? So for PDFs, probability distribution functions, taking the integral from negative infinity to positive infinity has to be 1. And then because it has to be 1 here, we also have a criteria that the limits at plus and minus infinity, it has to go to 0. If it doesn't go to 0 at infinity, then this first one can't be the case. Right? It has to go down and start approaching the axes as you go to infinity, because if it drifts up, then taking the integral from negative infinity to infinity is going to give you infinity. Right? So in order for this to be the case, this other one has to be the case. And this actually puts limits on the types of functions that you can have. They have to fit both of these. This top one, we can actually have a normalization constant that allows us to give it to 1. But the second one puts a limit on the types of functions that can actually be distribution functions. A cumulative distribution function is related to a probability distribution function. Instead, for a probability distribution function, you typically say, what's the probability between these 2 points? A cumulative is, what is the value below this value? So what's how many people are shorter than, 5'8", right? It's not how many people are between 5'7" and 5'8". So 5'7" to 5'8" would be a probability distribution function. Below 5'8", you're talking about cumulative distribution function. So cumulative distribution function goes from 0, comes up through where the peak would be, and then levels off at 1. Yeah, so examples of this would be people less than 1.5 meters tall, percent of students less than 20 years old. It's some value, and then you're counting everything that's less than that. Okay, so we can use probability distribution functions to find what are called expectation values. So let's say y is equal to x, and we want to know what the average y value is. And x is we have a probability distribution function for x. The way you would find the average y value, and we're going to use the symbol. Unfortunately, this gets used a lot. So we're going to see that this type of symbol has multiple uses. But when there's a single thing in it, like y, this is equal to the average of y. So this we use to mean average. Some places in math, you might see it with a bar over it for an average. That bar gets used for a lot of other stuff. And so we're not going to be using that because I think it ends up making it confusing. Because if you remember, Heisenberg was using matrices. This symbol also gets used for matrices. And so I want to refrain from using it. Just so if you're looking up stuff and you find a site that's using Heisenberg's method, it doesn't cause confusion. So we're going to use these greater than and less than brackets. If they're surrounding a single thing, it's meaning average. On a test, if you have a question, is this meaning average? Go ahead and ask, and I'll let you know. Okay, so the way that it gets applied to find it is you take your x times the probability distribution function, and then you integrate that from your lowest possible value to your highest possible value. In some cases, this will go from 0 to infinity, or from negative infinity to infinity, or if you're talking about people's heights, people don't get up to infinite height, right? So you go to the tallest person in the world would be your upper limit, and then you don't have negative heights, so it would be from 0 to 8 foot tall or whatever. Okay. So let's say y is equal to 2x. If you wanted to know the average of the y values applied across a set selection of x's, you take the integral from your lowest value to your highest value of the part of the function that you're interested in. Over here, y was equal to 2x. So we got the 2x here times the probability distribution function that tells us the probability of a given x value, dx. You take that integral, and that will give you the average value of y.
So the probability different, the PDF will be given, right? The
Yes.
function will be, yeah.
Yep. X squared, the x squared goes here, times the probability distribution function, take the integral. So you can sort of see that there's a pattern. If you have a function, and you want to know what the average value of that function for a series of x's is, it would be y, your average y value would you take the functional form here, multiply by the PDF, take the integral from your lowest value to the highest, that returns what is called the expectation value. It is the expected value, also known as the average value. And in more statistical terms, it's called the expectation value. Okay, so when you're looking in your book and they're saying this is the expectation value, this means the average value. There's a bunch of different terms, mean, mode, and root mean squared deviation, the root mean squared, not root mean squared deviation, we're not there yet. So the average value, if you have individual values, if you're taking the average, this would be 1 divided by your total number, right? you take the sum of all your x values, divide by the total, that's classically your average. If instead you have a probability distribution function, it's you're taking your x times the distribution function, integrating from your lowest value to your highest value, and that will give you your average value. Right? So whether you have a functional way of expressing how the x's are distributed, which would be your probability distribution function, if you have that, you're going to do this. Otherwise, you'd probably do the older fashion. The root mean squared is the average of the squared value. Right? So it gets used a lot if you're talking about like the average velocity. You know, if you're trying to do kinetic energy, use the root mean squared velocity because kinetic energy is 1/2 mv squared, and so you're interested in the v squared, the average v squared value. If you take the kinetics and thermodynamics class here, you'll see that squaring this and squaring that, or sorry, squaring this is not the same as squaring that. And actually, if you try the two values, you'll see that they're actually a difference between them, right? So to come up with a root mean squared value, if you have only a couple data points, it would be 1 over your total number times the sum of the value squared. So you first square the value, add them all up, divide by n. That is different than if you take this one and squared, and you can sort of see that down here you would end up, if you took this and squared it, you'd end up squaring the 1 over n, whereas here it's just 1 over n. Plugging it in using a probability distribution function, it would be x squared times the PDF integrated from your lowest value to their highest value. Right, so this is the root mean squared. A lot of times there are values that we want to know the average of the squared value, and so that's how we find it. The mode, we're going to also use this one a lot, is the most probable value. Right, so the most probable value would be at the top of the peak. If you remember from calc, the way we find the tops of peaks or the bottoms of troughs is we take the first derivative. Right? And wherever it's 0, that is the peak. It would also be where the second derivative is positive would be a top, second derivative is negative would be a bottom. Okay? So if you're asked, you know, what's the most probable location for a particle, right? And as we had said, the square of the wave function is the probability distribution function. So you would then look for the peak. And the way you'd find the exact value is you take the derivative of the function where that's equal to 0, that's your peak. That's the most likely spot of finding maybe the electron in the hydrogen atom. So that's how we tell where it most likely is, but we can't actually say where it is. We say it has the highest probability of being here, but not that it is there. There's a difference between the two. Okay, so we're talking about the implications. In one-dimensional space, if we go along the x-axis, the probability of finding an electron, for example, is in a narrow region, finding the electron in a narrow region between x and dx would be the probability of finding it is the wave function squared times that small interval at the particular location that you're interested in. In three-dimensional space, it wouldn't be a sliver of, between one x value and another x value. It would be between x and x, y and y, z and z, and so you're talking about a box, right? So this is where some notation that we're going to be using again and again comes into play. And this comes down to depending on where you're looking. So we will primarily be using d tau to mean the dx, dy, dz. Right? Some places also use dv because it is essentially talking about a box. So you could think about it as d volume, but because we're going to be switching between polar and Cartesian coordinates, a lot of times, and this v, whether you're talking, volume of, a gas, I find that it gets confusing. So we're going to be using d tau to mean combining dx, dy, dz. The reason we do that is when you're doing a whole bunch of writing down integrals, you can imagine that it gets kind of redundant or repetitive, saying, you know, your average A is equal to the triple integral 0 to infinity, 0 to infinity, 0 to infinity of f of x, y, z, dx, dy, dz. Instead, what we're going to do is say this is equal to the integral of f d tau. Means the same thing, it saves us a heck of a lot of writing. And if you're doing a proof where you have, you know, like 15 lines, that's a lot nicer to do than the one above. Right? They're essentially going to, when we're doing it, we're mentally thinking they mean the same thing. So this d tau takes the place of dx, dy, dz, but we use it so that we don't give ourselves a wrist cramp when we're writing everything down. Okay. So this is a slide that isn't in the original set of lecture notes, but is in the ones that I have recently uploaded. Okay. Complex numbers. It might have been a while since you've dealt with complex numbers. I think they touch on them in like, what, 10th grade math, briefly, but you never see it again. So, that's fine. Complex numbers, there are real numbers and imaginary numbers, right? The difference between a real number and an imaginary number, all the numbers that you're currently familiar with, those are all real values. An imaginary number, in some cases, it's helpful to be able to take the square root of a negative value, right? But if you remember from math, that causes problems. You can't take the square root of a negative value because positive value and negative value, when you square it, you get a positive value, right? But in some cases, like if you're doing the quadratic equation, there are some instances where what's inside the box gives you a negative value before you take the square root, right? And so historically, your instructors would have called that undefined. It's not undefined, it's actually an imaginary number. And the reason it's called imaginary is because there's no number that actually has, you know, that isn't an actual number. So what we would do, or actually let me be closer to this one. Let's say our value A is equal to the square root of negative b squared, right? So via math, A is equal to the square root of negative b squared. I'm chucking a set of parentheses around here to be clear so that I'm squaring b and then taking the negative of it, not squaring negative b. Right? So it's square and then cause a problem in terms of taking the negative. We can split this up into being the square root of -1 times the square root of b squared, right? Perfectly valid math, essentially just pulling two parts away. So this would be equal to the square root of -1 times b, right? The square root of the square, you get back your number. That is the problem. We solve that problem by calling this I. I for imaginary. Okay? So this then would be b times I. Typically the I goes at the end. So if you're having a string of things that are being multiplied together, the imaginary component most of the time you're gonna see it put at the very end of the line, right? So, the value I is equal to the square root of -1, so if we take I and square it, we get back -1. So essentially, you know, I squared equals -1. We're gonna be using this a lot. It's works out mathematically. So if you have a complex number, so A here would be called a complex number. It has a real part and an imaginary part. The form that we put them in would be, you have A is equal to two parts, the real part plus the imaginary part. And for real, you'll see a whole bunch of different symbols. This one is a really fun one to try to draw. That's used for real. And then typically, I've seen a lot of places where the imaginary is like a bolded I, or IM for the imaginary. When you're writing out one of these complex numbers, if it has a real set of values and an imaginary set that are combined together, the real come first, then the imaginary, and the imaginary is times I. Okay, so let's say we have a value A, which is equal to 2 plus 3I. With the imaginary numbers, there's this weird thing called the complex conjugate. Right? The complex conjugate is you take your imaginary component, so you take the function as it currently is, and then you just flip the sign of the imaginary component. It gets used a lot mathematically, and there's a lot of stuff that we're going to be doing with it. So it's sort of just a mathematical tool that we end up using. So let's say A is equal to 2 plus 3I. The symbol that we use to denote that we're taking a complex number and doing the complex conjugate, which is flipping the sign on the imaginary component, is putting a star typically to the up and right of the variable. Right, so this is our regular complex number. This is called the complex conjugate of our number. This would be equal, the real component is the exact same. Your imaginary component is virtually the same. The difference is you flip the sign. So if it was added together, then it's subtracted. If it was subtracted, then it's added. The difference between the complex number and the complex conjugate is you swap the sign that you're using. What this does for us, or the reason that we use it, is we can take the imaginary number, the complex number, times its complex conjugate, and we get back the real value. So anytime we take A complex conjugate times A, that would be equal to our A value. So that's, so we start out with our complex conjugate, 2 plus, minus 3I, and then that would be times 2 plus 3I. Alright, so we distribute this out, that gives us 2 times 2, 2 squared, 2 times plus 3I, so that would be plus 6I, and then 2 times negative 3I, so that would be minus 6I, and then the negative 3I times positive 3I, so that would be, plus negative 3I times plus 3I. So this part here would be 9, or negative 9 times I squared, and I squared is negative 1, so times negative 1. So this part here would be plus 9. So essentially, the plus 6I and the minus 6I cancel each other out. So that's 4 plus 0 plus the negative of -9, which is +9, and so we get 13 back.
So I squared is always -1.
I squared is always -1. That is the definition of I. I is the square root of -1, and so if we square it, we get -1 back. This is, this is one of the things that trips up a lot of people with quantum mechanics, is the idea that we have to use this thing called imaginary numbers. Not exactly sure why they're called imaginary numbers, the term imaginary number, where that comes from. It's just something that when you square it, you get a negative number. And so we can pull out, like we did here, right? Here, we pull out the square root of -1, and then we get the normal number that we know how to work with, and it ends up working well. Okay? So, complex number has a real component, has an imaginary component. They're going to end up looking like functions when you write them out, because we have to separate the real component and the imaginary component. So they're going to look like functions, but they're not functions multiplied by any sort of a variable. This I is not a variable. It is a constant. It's a square root of -1. Any questions? It's okay. As we use them, if you have questions, just stop me and ask, or swing past my office. Okay, so if we're talking about the wave function, there are some constraints on the wave function, which actually helps us. The reason it helps us is that there's only certain types of functions that can be a wave function, and so we don't have to look at all the different varieties of functions. They're very defined in what they could possibly be. It's a probability distribution function, right? Which means this has to be the case, right? We said that the square of the wave function and some of the wave functions have complex numbers. So we would be doing the real components of that wave function, which is essentially what we were just doing here, where we took the value times its complex conjugate. We ended up with a real number at the end, right? There's no I in our answer. So if you take the function that could have complex numbers in it, times the complex conjugate, essentially that's your way of getting rid of any imaginary values. Take this times some other constant, that's equal to 1. So this is a probability distribution function. This n squared is called the normalization constant. The reason it's there is to make it so that once you take this, the integral, you get 1 back at the end. The way that you're going to find what this value is, do this integral, and then 1 over that is essentially what n squared is equal to, right? And the reason it's n squared is because you get 1 of the n's from this one, 1 of the n's from that one, right? And so normally the wave functions are pre-normalized. So it would be the wave function divided by n, and so when you multiply them together, it and its complex conjugate, you get 1. You don't really generally see this n squared. It's integrated into the wave function, but technically or realistically, it's actually outside when you're trying to develop the wave function the first time around. Okay, because it's a probability distribution function, there are bounds on it, the same as when we were talking about a probability distribution function, right? The wave function, because when we square it, we have a probability distribution function. The limits that apply to all probability distribution functions have to apply to the subsample of the wave function, which is the probability distribution function. So another one is the upper and lower limits, plus infinity, negative infinity, or 0 to infinity, depending on your range, has to be equal to 0. If it's not, then this won't be the case, and so that causes problems. The other one is that the wave function and its slope have to be continuous and have to have a single value. Single valued means that, well, let's go through them. Continuous means that there's no break in the function, right? So this one here would be a non-continuous function. The value jumps, and yeah. This one here, while it is a continuous function, the slope or the first derivative is not continuous. It jumps. You can't have that. This one here, you have multiple values of y for one value of x. If we're talking about the probability of finding something in a place, you can't have three different probabilities. It's one probability for finding it at this location, and so it should have one value. So that's what single valued means, is not this. I have a function that only has one y for every x. And then this one you also have to add, well, this one's the derivative and the value are not continuous. Right? So this slopes up, non-continuous functions. So essentially you need something that looks like a nice, smooth, curvy line. That's what all this is. The nice thing about that is it's going to limit the number of functions that we have to worry about. Right? There's only just so many that follow, particularly these two, cull down a whole lot of them. Right? You couldn't have x squared, for example, because it goes to infinity on both sides. Right? So it really limits the number of functions that we can have. This continuous and single valued also limits the number of functions. It might sound complicated, but it makes your lives a heck of a lot easier having these restrictions on possible wave functions. Okay, the term operator. All it means is a mathematical operation, something that you do. Okay? So operators are functions that work on functions. So you can think of like f of x is a function of x. An operator is something that does something to f of x. So you've actually been using operators since like the first grade, right? And they just never call them operators. So a couple common operators, 2 with a multiplication sign is an operator. It's essentially saying take your function and double it. So 2 times is an operator. So let's say h, we're going to use it as hat. A hat above what would appear to be a variable, and that's saying that this is an operator. This is a mathematical tool. Try not to use the word operator when describing operator. Okay, so we're going to put a hat over some variable looking thing, and that is going to be what we represent as an operator. It's a function that applies to a function. Okay? It applies to whatever's directly next to it. So hx is an operator h doing something to x. Common examples, 2 times x would be doubling the value of x, h would be 2x. So if we had the operator h is equal to 2x, or 2 times, and then we had hx, it would essentially be saying, take this, replace it with 2x, so it would be 2 times x, or doubling x. The square up here, the exponent, is an operator. Doesn't really behave this all that well, but go with me. The exponent is an operator involved with taking the value and multiplying it by itself, right? So this means something, and that in essence is an operator. The square root symbol is an operator. It says take the square root of whatever's next to me, right? So these are all operators. It's just we're going to be using some stuff that you haven't used before that don't have common mathematical symbols for them. And the way that we're going to denote something as being a function that operates on a function, aka an operator, is with that hat, which is another reason why we're not going to use a horizontal bar for meaning an average, because there's not a heck of a lot of difference between a hat when you draw it and a horizontal line, unless you're really careful about how you draw it. So, other operators that do work on functions, you could have the derivative operator. So you could have d f of x dx takes the derivative of the function. The way we would represent that is h bar dx, or we could have something a little bit more complicated where it says take your function, when you break it up into two parts, one where you multiply it by x, and the other part where you take the derivative of x and then you add the two together, right? So the h hat would be d dx plus x, and so you're essentially taking this and applying it to whatever function is next to it. So if we said let h hat equal d dx plus x, then we have h hat being applied to some function that would be equal to writing out d f of x dx plus x times f of x. The reason we do this is if we're doing some sort of long derivation, writing this out is going to get tedious if we can just replace it with this until we're ready to actually do the math. Okay? So an operator is a function that applies on another function. Operators are said, or two sets of operators are said to commute with each other if it doesn't matter what order you do them in. Okay, so we're going to look at some examples to give you a little bit better feel for these. So we'll do the first one as a class, and then you're going to do the second one individually. Okay? So first one, we have two operators. We're going to value them both and then look to see, do they actually commute? Does the order matter? So let's say we have any function, f of x. So a hat, so that's how you're going to call your operators, is you're going to say the variable name and then just say hat. So a hat is essentially the first derivative with respect to x. B hat is taking your function and multiplying it by x squared. Right, so it would be this times whatever's next to it. Okay, so our first one, a hat f of x would be equal to what a hat is, the process, which is d dx applied to f of x. B hat f of x, right, would be x squared times f of x. Okay, so when you're doing these operators, you do the rightmost one first, so they sort of go right to left. The operator applies to what's directly next to it, and then gives you an answer. And so when we have them stacked up like this, the order would be first A applies to f of x, you take that result and then plug that through the B operator. Okay, so if we're doing B hat A hat of f of x, B hat A hat f of x, this is essentially doing B hat applied to the result of A hat f of x. All right, you start from the right, move your way left. So the first thing that we would do, we're taking B hat times the result. A hat f of x was the d f of x dx, right? So we take that result, use that as a function to apply it to B hat, and so that would be x squared times d f of x dx. If we flip these two and do A hat, B hat, f of x, right? This would be the same as A hat times the result, or operated on the result of B hat f of x, like that. So this would be equal a hat operating on the result of b hat f of x, which would be x squared f of x. Okay, so here we have two different functions, right? So we're going to have to use the, a hat is taking the derivative. So we're going to have to use the product rule. The first times the derivative of the second plus the second times the derivative of the first, right? So this would be, 2x, so the derivative of the first times the second, plus the first times the derivative of the second. Okay, so you can see that the order matters, right? If we do b hat a hat f of x, we get x squared times the derivative. If we flip the order and do a hat b hat f of x, we have this as added term. So this would be said to not, these do not commute. A hat and b hat do not. They do not commute. It matters which order you do them in, right? It's not going to be the case of all functions. Okay, so I want you to do the same set. So a hat function, b hat function, ba function, and then a hat b hat function applied to these two operators. So this one is, instead of multiplying it by x squared, multiply it by 10. And